We're going to look at a very cool trick for expanding polynomials that will be useful not just in this class, but any math class after this, because it gives us a shortcut from doing a lot of work. Okay, and I'm going to skip down to here before we get into calculations and show you that it's about expanding binomials. So if I have binomials that are raised to the second power, you know how to do that really well, right? We could take x plus y, right, and multiply that by x plus y using our box here, right? And we would end up with, of course, x squared, xy, xy, and y squared, right? And as we know, in the center you get two of these right here and right here, hence why there are two xy's. And then of course we have our x squared and we have our y squared. Right, so we know how to do this as second power, and of course we could also take this answer and multiply it by x plus y with another box and get the next answer. But that would take a lot of work if we needed to get to, let's say, the fourth power, fifth power, 10th power. Right? So what we do is stand back a little bit and notice if we just remove all the variables that there is a pattern that forms with all the coefficients. Right? If we just have coefficients of 1 for both the terms inside, well, it just comes out to like for a quadratic, a 1, 2, and a 1. Like 1x squared, 2xy's on the diagonal, right? And 1y squared. If we did that to the third power, if we took this and multiplied by x plus y, we'd find out, well, it goes 1, then, well, 1 cubed, 1x to the third power, then 3x to the second, y to the first. Let me write those down, right? So this is what it looked like. It'd be 1x cubed, right? And then 3x squared, y to the first, and then 3x to the first, y to the second, and then 1y cubed. Right? That's what, just like we see here, right? So these coefficients just represent the numbers that would show up here anyway, and we can see there's a nice little pattern on how they form. You can see that the first term and the last term are always going to be 1, like they are here, 1x cubed and 1y cubed, right? And then these are called triangular numbers because all we have to do to get all the numbers on the inside is just add the two adjoining numbers. So this 1 plus 1 gives us 2. And this right here, 3, is just comes from 1 plus 2. So we can add up any two numbers triangularly, right? 4 plus 6 gives us 10. So it's a very cool tool to easily create to find out what the coefficients would be without really having to do the box method, let's say 4, 5, 6 times to find out how to raise something to the 5th or 6th power, right? So we want to figure out how to get these numbers without having to really do everything the long way anymore. So a very cool tool. So a cool thing to notice is that we can do this as long as we want. Yes, it could get a little long, but it's always going to be faster than really doing it manually by doing boxes after boxes after boxes. Okay? So this has a probability connotation as well. So in this format we call it Pascal's triangle, and that who discovered that this pattern existed and found a shortcut. And it also applies to, right up here, to probability. Right? And there's this formula here, and it's a completely different formula. You might remember this from some probability that you have been exposed to before. So this right here, this exclamation point means factorial. And that means factorial. Which simply says, let's say 3 factorial is going to be 3 times 2 times 1, and you always finish on 1. So 3 factorial is actually equal to 3 times 2, which is 6, times 1, right, which is the same answer, right? And we have two different numbers here, one on top, one on the bottom, and what it stands for, right, like something like this, probability-wise, say it means, say you have 6 items how many different ways can you choose 2 of them? So often this is read 6 and choose 2. 6 choose 2. And if we do this formula, right, according to the right up here, would have 6 factorial divided by r factorial, that's the bottom number, and then n minus r factorial. So you just subtract these two, top minus bottom, 4 factorial. And this answer will give us how many different ways there are if you have 6 different things just to choose two of them, right? Because you can choose the first and the second, the first and the third, the first and the fourth, first and the fifth, first and the sixth, and then go back and say, well, I want to choose the second and the third, the second and the fourth, the second and the fifth, the second and the sixth, right? You can keep on going and counting those up manually, but this formula is a nice, concise way of getting you the answer. So what we'd have to do is write out this and figure out what it equals. Now there's a little math to this that would help us out. So if we know ahead of time, if we're trying to cancel things out, we could say, well, 6 factorial is 5. Well, 6 times 5, and then times 4 times 3 times 2 times 1, which is 4 factorial. Right, now I want to write this way because we can cancel out with the 4 factorial that's on the bottom. Right, so now we'd have 2 factorial, which is just 2 times 1 from right here, and then we have this 4 factorial. So just like in the old numbers, we know 4 times 3 times 2, right? Yes, it equals, let's see, 4 times 3 is 12, times 2 is 24. See, both of these just equal 24, so we can cancel them out just like regular numbers. And then we have 30 divided by 2, which is 15. So it means if we just counted them manually, how many different ways there are to choose 2 items out of 6, there's 15 different combinations, right? So this C often is called combinations, right? And we're choosing how many combinations are there to choose 2 things out of 6. Nothing more than that, right? Now this corresponds right here, 6 choose 2, this number would actually be on the 6th row down. This is row, say, 4. This is row 5. I go down here, 5, 6, right? This will give me the second spot, right? Or second place, we should say, not spot, but second place. And I should get a 15. And you'll notice if I keep doing this pattern, I'll get 1, and I'll get 6, I'll get 15. And you might say, wait a minute, this was the second place. How come it's the third number? Well, these are all choosing 0. So you notice how this started on 0? Well, these are all 0. So technically this is 0, 1, 2, and that's why it's 6 choose 2. 6th row and the second location, which you got to remember you start with 0. So as long as you remember that, you can still use Pascal's triangle to get 15, or you can use this formula. Now you don't have to memorize this formula. This is in the calculator as well. So let me show you in our calculator here where to find it. So let's make this a little smaller. All right, if we go to math, and we're going to go over to probability, you can see the third choice down here. There's one with a P, one with a C. We want to use the combination. Choose that. And then you can just type in those 2 numbers, 6 and 2. Alright, 6 and 2. And that will do the formula for us, 15. Right? And we can also do this on decimals. Let's pull that up. Right here. And I already kind of set this up here, but if you open up the keyboard and go to functions, and you go all the way down to the very, very bottom, the very last choice is going to be that. So if you type that in somewhere, let's do that. And what you do for this, you just type in the number separated by a comma. So 6 choose 2 would be 15. So 2 ways to do that, either calculator or graphing or decimals. Yeah. And what I said up here earlier was just something that's kind of shortcut that I could just do these and say what the top number and bottom number were, and they can just give us the coefficient that way. So it's kind of easy to figure out what the coefficients are just by moving these back and forth. Okay? But like I said, don't have to memorize this. It's just something that is going to be useful for you. You can always use the calculator to figure out how to do these calculations. But one day you might take a statistics and probability class and just maybe have a little bit of practice here. So let's go through and do the rest of these. So if we have 9 things and we're trying to choose 4 of them, right? So that'd be 9 factorial divided by the 4 factorial. So you notice the first 2 here are just these 2 numbers, right? The same ones with factorial, and then the remaining one on the bottom is just the difference. So that's 5 factorial. Just like that. And we usually just take the top one and we write it like we did last time. We'll just do 9 times 8 times 7 times 6, and then we get to 5, we'll write 5 factorial, so again it'll cancel out. So there's always a pattern here on how we solve these. So I'll get to here and then I'll stop basically when I get to the number that matches the bottom. And then I'll have 4 times 3 times 2 times 1 times factorial. Right. So 5 factorials cancel. And then whatever's left over, try to do some canceling as well. Let's make this a little bigger. Right, so, and you could do this many ways. So I can take 4, and that will go into here 2 times. I could take 3, that goes into here 3 times. I can take 2, that goes into 6 3 times. And then I know my answer is 3 times 2 times 7 times 3. Right? Now you could just put this in the calculator, of course, but there is a way to do this manually as well. Alright, choose 3. Now think about this instinctually before you calculate it. If you have 3 objects, how many different ways can you choose 3 of them? Right? If we have 3 things, how can we choose three of them, right? So our intuition says that should be 1. If you have 3 objects or 3 things, how can you choose 3 of them? Right? Like if you had an outfit with like a top, a bottom, and shoes, and you only had 1 top, 1 bottom, shoes, and you had to choose all, you had to have 3 of them, there's only 1 outfit, right? There's only 1 way to do that, right? And the calculations here will prove that as well. So if I do top and bottom the same, and then the difference is 0, well, that will come out to be, well, those cancel out, and 0 factorial by definition is 1. Very similar to how 1 to the 0 power is equal to 1. Because you might say, well, 0 factorial, how can that equal 1? There's some math behind this and why it's true, and it's similar to this reasoning. So we really get 1 over 1, which equals 1. Now, one little sidebar here that's not here is, what about choosing 0? What if you had 3 objects and you chose 0? Well, that also equals 1. You might say, but I didn't choose anything. How could I, if I had 3 things and didn't choose anything, how come the answer is 1? Well, this is the philosophical equivalent of saying, well, not making a choice, 0 choices, is a choice in itself. If you don't make a choice, you still made 1 choice, that is, not to make a choice. So, logically, it does actually work. So that's the background on this. There's a couple ways of doing it, one with this probability formula, and one with this Pascal's triangle. And of course, either way can just be used in a calculator. So what we're going to do is practice just expanding, using this formula. And this notation just says, well, we can do this as long as we need to. So if this is the 10th power, we can say to the 10th, 1 less, to the 9th, 1 less, to the 8th, and then ... keep doing that until you get down to n to the 1st power, and then eventually n to no power, to 0 power. So you just keep doing this until the exponent disappears and goes to the 0 power. Okay, and so we can practice that here, and we can do it a couple ways. Right, one is just by first expanding and saying, well, I'm going to the 3rd power, right? So I'm going to be using my row right here, 3rd row down. Sorry. Yeah, 3rd row, 1, 3, 3, 1. 1, 3, 3, 1. So I already know I'm going to use these coefficients. It's going to be 1, 3, 3, and then a 1. Okay? And all I have to do is write out these in descending order. So the first one's going to be x to the third, and then x to the second, and then x to the first, which is just x, and then x to the 0, right? And, well, we usually don't write x to the, well, let's leave it there for now. And then I have to write out this, right? So this is going to be -2, and that's to the third power, and -2, and that's to the second power, -2, and that's to the first power, and -2, and that's to the 0 power. So the first term starts in front and goes in descending order, and the second term starts in the back and goes the other way. And you notice how the exponents always add up to 3, being a third-degree polynomial. And then finally, right, we have our coefficients that we add on to it. So we're going to have a 1, a 3, 3, and a 1. Okay. Now, I didn't put any signs here, pluses, minuses, because that's dictated by this power of -2. So when I have a power of, like right here, power of -2 is to the 1, so I'm going to get a minus sign here. Right? And when I go get over here, power of -2 is to the second power, so I'm going to get a positive. So the pluses and minuses are determined by the terms themselves. You don't need to put them in ahead of time. So we're going to end up with, let's see here, this is going to be 1 x to the third, and then times 1, right? That's to the 0 power. And then we're going to have 3 x to the second, and then -2 times the first is -2. And then we're going to have 3 times x to the first, or just x, and -2 to the second is times 4. And then finally we'll have no x at all, and we'll just have -2 to the third power, which is -8. And finally, when we simplify all this, we'll get x to the third, and we'll get -6x to the second, right? 2 times, -2 times 3 gives me -6. And then I'll have plus 12x and -8. All right, so that is the expanded form of doing this, and that would be the same as if I did x minus 2 times x minus 2, did this box method, then I got that answer, and then I multiply it by x minus 2 as well, right? But once you get the hang of this, you'll find out it's way faster, especially with a calculator, and especially for higher exponents, like if we go to the 5th or 6th power, you know, way faster than trying to do boxes over and over and over and over. Okay, so let's just try a few more of these, and that's all we're going to practice on here. Okay, so fourth row. Okay, fourth row. Okay, we're going to go fourth power. So we have row 4. Remember, we started 0, so technically it's the 5th, physical row down, but it's the 4th row. Row 4. 1, 4, 6, 4, 1. So those are the coefficients I'm going to use. 1, 4, 6, 4, 1. And then from here, it's just about giving yourself enough space and try not to clutter it too much. Right? So I'm going to start with 2x, and it's going to be to the 4th power. Right? So I'm going to start with 2x, and I always like to do parentheses, be careful. 4th power. Leave a little space. 2x to the 3rd power. I'm going to keep going until I get to the 0. 2x to the 2nd power, and 2x to the 1st power, and then 2x to the 0. Okay, so I did that all the way through. Alright, so now I can do the second term. So that's going to be -3 to the 4th power, and I work my way backwards. -3 to the 3rd power, -3 to the 2nd power, -3 to the 1st power, and -3 to the 0 power. And then finally include your coefficients. I'm going to have 1, 4, 6, 4, and 1. And the rest of this is all simplifying. So I'm going to actually take my time a little bit more on this, as the terms are a little bit more involved here. What I mean is that right here, 2x to the fourth power, well, that's 2 times 2 times 2 times 2, right? That's 2 to the fourth power. So we get from here alone is going to be 16x to the fourth. Then we'll have 2 to the third to x to the third, right? So that's 8x to the third. We'll have 2x times 2x, that's 4x. And then just 2x by itself. And then 2x to the 0 is 1. Okay. Then repeat. We have negative 3 to the 0, of course, is 1. Negative 3 to the 1 is negative 3. And we have negative 3 squared, that's 9. Negative 3 to the third is going to be negative 27. And then lastly, I'll have negative 3 to the fourth power, that'll be positive 81. And finally, I can go through and simplify all this. All right, so I'll have 1 times 16 times 1, that's going to be 16x to the fourth. Have 4 times 8 times negative 3, going to need a calculator, right? Or maybe you just do 12 times 8, that's 96. So we have a negative 96 x to the third. And here we'll have, let's see here, 6 times 4 times 9. I put that in the calculator. Let's see here, I get 216 x to the, I forgot it. Did you catch it? I missed it, didn't I? That's the second power. I know that because these should be going down 1 at a time, 1 degree at a time. So since I missed that, I knew it went from 3 to 1, something was wrong. Very good. And then, keep on going. We got 4 times 2 times negative 27. In that calculator, comes out to negative 216 as well. Oh, I see it. Okay, good. And then lastly, we have just 1 times 81. That's positive 81. Now let's say you did not want to do this with the triangle and write that out. Remember, you can use your calculator, right, to get these coefficients, only that part. So if I need to get the 1, 4, 6, 4, 1, you might notice it's symmetrical. So really I just need to know what these middle terms are. And once I get to the middle, I can just mirror it. So let's see here. So remember, it's math, and right, and then go down to 3. And I could put in for every single number. Now it's 4. And we're going to do the 0 spot first. Of course, that's the 1 here. And then I can go back up here, rather than hit the menu all over again. It'd be easier just to go back up, hit enter, and then just overwrite that and hit 1. And then I get 4, and then just repeat that process a few times. All right, we get 2. And we get 6, right? So, and then once we get to the middle, or just right past the middle, right? We know it's going to repeat. So you could type in the next ones, right? You could do this. But there's always that pattern there. So you don't really have to type in every single one, because we know it's just going to be symmetrical anyway. But just for being complete here, I'll go all the way with it. All right? So we can get those same values, whether it's from our triangle up here, right, or from the calculator. Now, of course, if we were going up to the 15th row or something, making a triangle with that many rows would not be practical, and the calculator would be our option. Okay, let's say I want to find a certain term, but not the whole polynomial. Meaning, what if I asked you to find like the term that had x squared, and I just wanted to locate just 216x squared and figure out just this one term, and I didn't need anything else here. Right, we could work backwards to figure out what numbers and what powers to which one do we actually use. So we're actually going to do this somewhat in reverse to figure out the answer in this question. Because it says we have a x plus 3 to the 7th power, right? So this is going to go like the 7th power and the 6th power and the 5th power, right? So I can tell already that the x to the 5th power will be the third term if I did this all the way through. But I want to skip all that. I don't want to find the first term, second term, or anything after that. I just want to isolate and find the one part that has x to the 5th in it, right? So I just need to understand or remember how this works and where these numbers came from. So if I go back and remember the 1, 4, 6, right, that came from up here. Let's see, 1, 4, 6. Right, I can actually get this value right here by knowing it's the fourth row, and then remember we start at 0, so it's 0, 1, 2. So if I put in the calculator 4, choose 2, I can get 6. So I need to do that and adjust that for the 7th row, right? So I know this is going to be the third one, right? That's going to be like x to the 7th, and they're going to have an x to the 6th, right? So I know the coefficient here, the red part here, right? The number is going to be 7, right? And we're going to choose 0, 1, 2. Remember, always start with 0. So it's going to be that. Right? And if I work backwards for this positive 3 here, remember we work backwards, so if you look at this, all the coefficients always add up to the total here. So 4 plus 0 was 4, 3 plus 1 was 4, 2 plus 2 was 4. So I know that if I have x to the 5th, my second term here is going to be 3 to whatever exponent adds up to my full degree. So that's going to be 7. These two have to add up to my full degree. So this way I've just found a fast way of just finding the one term that has x to the 5th in it. And I just need to use my calculator. All right, bring this over here. I erased it, so I got to go back in the menu. Hit 3, and then I have 7. Choose 2. That's 21. Okay, so I'll have 21. Actually, I'll do red. That's 21. I have my x to the 5th. And 3 squared is just 9. And then finally I can simplify all this. 20 times 21, it's going to be 180 plus 9, that's 189, x to the 5th. So I successfully found the one term they were asking for just by using the properties we know and doing a little working backwards. Always remembering though that first term counts as 0 spots. So it goes 0, 1, I could write that in there. That goes to 0. This is 7, choose 0, and this is 7, choose 1. So that way, that's why this is 7, choose 2, even though it's the third term, 1, 2, 3. And that pattern will always be there. All right, let's continue down here. All right, in the expression 6, choose 2, what coefficient does this represent on the Pascal triangle? All right, we kind of did this earlier, I think. All right. Is that the one we did? Yeah. So we know it's 15, but now on the Pascal triangle we can see choose 2, 1, 2, third term, right? That's where the 15 came from. So this is just supporting this idea that even though it's choose 2, it's really the third number, right? It's the third number because it goes 1, I think it went 6, and then I think it went 15. So that's why the answer is 15 on here, right? And you could see from the triangle it's 15, and we could see from the probability calculation, have 6 items, choosing 2 of them. There's 15 different ways to do that. All right, so that's it. We're going to use this sparingly throughout this problem. Remember, you always have the calculator or Desmos to help you do these probability calculations. You just need to remember the pattern on how the exponents grow or descend on the first term and how they ascend going the other directions for the second term. And of course those degrees always add up to the degree we're working with. Okay? All right. We'll see you next time.